Okay, welcome everybody. Back to what we'd stopped with yesterday was our version of like D'Alembert's formula for the 3D wave equation. So what did this look like? Um, our 3D wave equation looks like this. This is the 3D Laplacian, of course. So we have wave equation on all of our three t greater than 0. We have initial data here, phi and c, so similar notation as before. Now, of course, x is a vector denoting a point in space, right, in R3. Um, and so the question here is, does there exist some kind of D'Alembert-like formula like we had in the 1D case? And there does. It's called Kirchoff's formula. I'm not going to go through the derivation of this. There's a couple of different ways this can be done. It's touched on in the textbook. You can actually look up the details of this, but it would take way too long, and it's not technically too involved for the course, but it kind of involves a detour into a lot of Calc 3 stuff that I'm not going to revisit right now. So if you're interested in derivation of this, you can have a look. This is in chapter 4. I believe this is the first section or second section of chapter 4. Is where you can find this derivation. What I mostly wanted to do though was look at what this formula tells us um, about the wave equation. So if you're interested, where the formula comes from, one way of thinking about it is kind of like a sketch of where this comes from is um, a change of variables can be made to transform this problem into a slightly different PDE, which is then solved in another way. And out of that rises this Kirchhoff's formula. But what does this actually tell us? So oftentimes what is done here to denote like the fixed uh, nature of an x and t. So remember, we're thinking about this as like, okay, for some fixed point x at some time t here in R3, I can find the displacement of the object in question of the, say, so I have some initial disturbance, right, in 3D now. I have an initial disturbance, an initial signal. Now, if I want to think about the propagation of this, right, so the displacement u at position indicated by x at time t, so think about those being fixed, can be determined entirely from the initial data phi and c. From this expression, where, forget about this for a second, right, this is some kind of averaging thing here, so forget about this at the moment. Okay, I am integrating here over this, the boundary of the ball centered at x with radius ct. Okay, this quantity, don't pay too much attention to this quantity right yet. And so I have to use a different dummy variable because the x is showing up in the center of this boundary. Okay, so I'm using a different dummy variable, y, to parameterize this surface integral. Maybe before I go on here, I'm going to do a little bit of notation, just in case you haven't seen it before. So a brief aside about some notation here. Um, so what is this thing? Let's say that x is a vector or point in Rn, right? So x is an n-tuple of real numbers, okay? What is this? This is, call this the open ball of radius r centered at x. Okay. Now, because maybe we want to use x as a variable, oftentimes if this quantity is, x is fixed, this is the center of the ball, r is its radius. If we want to use x as a variable showing up in an expression that involves this, oftentimes you'll see it written as this will be like an x naught instead. So b of x naught r is the open ball of radius r centered at x naught. Well, if I describe this in set builder notation, what is this, right? Of course, I've said here, if I've let x naught be, I'm going to, okay, we'll go ahead and let's just go all the way. Let's just add all these things. There, okay. So what is this? This is the open ball of radius r centered at x naught. Maybe I should include in Rn. Okay, there. Okay, so we can just do all of these at once. In set builder notation, what is this? This is the set of all vectors x in Rn such that the distance from x to x naught is strictly less than r. So in this textbook, you're going to see this written in the following way, typically. So whenever this shows up, this is playing the role of our length, regardless of what the dimension we're showing up in, right? So if n is equal to 1, this is just normal absolute value. If n is equal to 2, this is, your modulus or your distance. If you really want to, right? If writing it this way really bothers you, and sometimes, I could see how this is maybe a little bit confusing. Coming from Calc 3 or something, maybe having it written in this way seems better. So what does this thing look like? Of course, if n is equal to 1, what this looks like is, well, why did I draw this axis if n is equal to 1? Here, let's not do that. If n is equal to 1, I have a real line. Then say here is x naught, right? And then the ball centered at x naught of radius r would be this open interval, right? So here would be x naught plus r. Here would be x naught minus r, and this would be an open interval because of the strict inequality here, right? So this is the open ball. Okay. The closed ball of radius r can be written in this way. So the closed ball of radius r centered at x naught and Rn can be written like this. So the closed ball, I'm not going to write anything else. Okay, and of course, this is now this inequality has been replaced with a less than or equal to r. So in the n equals 1 case, this would be now a closed interval. Of course, let's look at some other dimensions here. All right, so in n equals 2, the open ball, right, maybe if here's x naught, then we'll say here is distance indicated by r. If it's the open ball, it's that thing. So this might be this. The closed ball, of course, includes this boundary. Right, this is the closed ball. And of course, you have probably seen this in some form by now. maybe even in this exact same notation. So here's open ball, here's closed ball. But it is advantageous to us for a variety of reasons, right? There's plenty of examples of scenarios where maybe I should do this. When I say this is the closed ball, what am I indicating? What points are included here? Right? So in the open ball, what points are included? It's all points that have distance strictly less than r from x naught. So all of this stuff is included, right? All of these points here are included, but the boundary is not. This boundary circle is excluded. That's a dashed line, right? So this boundary, the outside, is not included. But here, what's included? Well, everything including the boundary. Now, if this is the boundary of the ball, so this is the boundary of the open ball of radius r centered at x naught. And if this is the notation we use, then in set builder notation, this is the set of all x in Rn such that this distance is exactly equal to r. So in the n equals 2 case, the boundary is exactly this boundary circle, right? And that's it. It's only the boundary circle, right? So what points are included? It's only the points on the boundary, right? Nothing else. So if I were to draw that, so here's x naught, here's r. The boundary is just the points belonging to that boundary circle. Of course, if we do this for 3 dimensions now, here's a point x naught, and here is some point I've indicated r that is like a radius, then the open ball, right, would be a 3-dimensional ball, right, in this way. Okay. If I were talking about the ball, right, if it was an open ball, it wouldn't include the boundary, which is now a sphere, right? It would include all of the points inside of it, but not the boundary. If it was the closed ball, it would include all of the points, including the boundary sphere. And if it was just the boundary, it would be only the boundary sphere, right? No points inside of it. Okay. So notice that here, this is a circle, right? Is a circle in n equals 2. And it is a sphere in n equals 3. And remember, when we talk about sphere, we are talking solely about the boundary, no inside points. If we want to include the inside points, we wouldn't call it a sphere, we would call it a ball. Okay, that's what we're going to do for the rest of the course. That's the terminology we're going to use. Okay, you might notice that if you take the open ball and throw in the boundary, it is the closed ball, right? So as a little aside here, this closed ball, right, is just the open ball together with its boundary. That's it. Okay. right, so that's the first thing I wanted to go over. This is some, this is some terminology. This is some stuff we're going to be repeating throughout, like the rest of the course. So it's nice that you've seen this in some way. Again, the idea here being that when I say ball, I'm talking about all of the points inside, right? And either including the boundary or not, whether it's an open or closed ball. When I talk about just the boundary, I'm only talking about the boundary points, right? I'm not talking about what's inside of it. So why does all of that matter? Well, let's go back to Kirchoff's formula that I have written here. Well, the reason that matters is because the way that Kirchoff's formula is written down, this is an integral over the boundary. Now here's some other notation, right? The notation we're going to use is, rather than like go through the kind of like Calc 3 notation that's used for surface integrals, basically we're going to write integrals down, and if the set showing up under the integral is a surface, then you know that that is a surface integral that you're doing, right? So I don't have to actually come up with the parameterization and plug that stuff in. It's just that you know, because I'm integrating over the surface of a 3D ball, or sorry, the boundary of a 3D ball. That is a surface. So this is a surface integral. Okay, so this is a surface integral. That is, it is an integral of whatever resulting, thing I have here, right? I'm integrating that over a surface. Okay, so not the interior points of this ball, just the surface. Okay, just the boundary. Okay, now to help our intuition, we're going to replace this x with an x naught. And that's, again, I'm not doing anything here. All I'm doing is I'm trying to emphasize the fixed nature of this xt in this expression. Okay, so rewriting Kirchoff's formula. I'm going to rewrite this as the following. So the displacement at a fixed point x naught t is 1 over 4 pi c squared t squared times the integral over this boundary of the ball centered at x naught of radius ct of the quantity. Now that I've used x naught here, that frees me up to use x as a dummy variable here. This is phi of x plus gradient of phi of x dotted with x minus x naught plus t times c of x naught, or sorry, not x naught, x ds sub x, again to indicate that this is a surface integral here. So here's Kirchoff's formula. Okay. So first question. So question 1. Does this even solve the 3D wave equation? The 3D wave equation, what we called asterisk here. Does it even solve this with initial conditions phi and c? Okay. So first of all, does it solve the 3D wave equation? The answer is yes. I'm not going to check it here, but it does. The second question is, what about the initial conditions? As we noted in yesterday's lecture, there's some issues here, right? Unlike what happened with D'Alembert's formula, where we could, like the initial conditions, you could just plug in t equals 0 and immediately see that what happens is that phi and c immediately pop out of it for the initial displacement, initial velocity. And so it was very clear to see that it solved the initial conditions. Here, I can't even plug in t equals 0 because of this t squared in the denominator outside here, right? It doesn't even look like it's defined here. And so what about these ICs? The answer is, what I need to check is, since I can't just plug in t equals 0, what do you think I'm going to do? I need to check a couple of things. I need to check that the limit as t goes to 0 from the right, t is, let's look here, t is greater than 0, so I only need to check the one-sided limit, the one from the right. So as t goes to 0 from the right, and as x approaches x naught, this u of x t is equal to phi of x naught, and the limit as t goes to 0 from the right, x goes to x naught, of u sub t x t is c of x naught. This is what I need to check. Because if these limits work, then what do I do? So if these work, I simply define u of x naught at 0 in such a way that makes this match up with the initial data, right? So what do I do? Right? The idea is that I want to extend them by just defining them to be the initial data at t equals 0. Right? So to be the initial data at t equals 0. If I do this, what happens if these limits hold true and I just define my u to be the initial data at t equals 0, I get a continuous u. Okay, a continuous u at t equals 0. If these things hold. So I can define my initial displacement, initial velocity to be these functions. If these limits hold true from this formula, or if these limits hold true in this formula, then if I define u to be this formula everywhere else, not at 0, then taking this formula together for everywhere t is not 0, and at t equals 0, I'm just defining it to be the initial data, then what I have is continuous, regular enough solution defined by this formula that solves the PDE and solves these initial conditions, or satisfies these initial conditions well, because I've defined them to do this. So I better hope that these things work out. Now, what I'll do is I will show you how this one's done. So let me, rather than write this out, I'm actually just going to show you exactly where it is in the textbook, because it's nicely contained in a single place. So give me 1 second to find it. Let's see here. Aha. So this is under the section attainment of the first initial condition. So here's the limit that's being taken. Now he's already replaced the limit with x here, whatever. That's okay. Just forget about that for a second. The limit as t goes to 0 from the right of this expression. So here's just Kirchoff's formula. So this is just rewritten. Here's this limit. Break up the integral in Kirchoff's formula into 3 pieces and consider these limits separately. Okay. There is a lemma called the averaging lemma from the appendix. I'm not going to quote. You can look up that lemma. From the averaging lemma, the first and last piece of this integral work out to be exactly phi and c. Okay. So that this third expression, so the first works out to be phi, the third works out to be so this is c, so the third limit, this limit ends up being 0 as t goes to 0 because of this t multiplying it. And the second limit has to be, you have to do this estimate here, okay, where you move this inside. I'm not going to go over too much of these inequalities here. So this is Cauchy-Schwarz. And I obtain this bound, which allows me to obtain this bound, and by the averaging limit I get 0. You can also do the second limit if you like. That the arguments used there, that's a nice trick, but it's not something we're going to refer to too much. We're not going to have much need of it. But that's basically how the limiting argument is taken care of. And so you see how a lot more care has to be taken here, even to just say plug in your initial condition t equals 0. A lot more care has to be taken. Now, what is it that's actually going on here? What does this formula tell us about what's happening? So let's ask the exact same questions that we asked in the 1D case, now in the 3D case. So what do I mean? These questions about causality, right? Like from D'Alembert's formula, since this formula allows us to define our solution to this equation at any position, any time. Any question we want to ask about the displacement at some fixed x and t, we should be able to answer in terms of that formula, right? That formula is entirely in terms of a surface integral over an expression that involves only the initial data, right? So here's a question, just like we asked before. What is the domain of dependence? What about the domain of influence? To see this, what is it that's going on here? So let's bring back Kirchoff's formula. So if Kirchoff's formula, the displacement at a position x0 and a time t is given by this formula. Again, don't think of the specifics too much. It is some kind of like averaging thing. Okay. In fact, like if you look at what this thing is, right, you may immediately point something out. Right. So what do you notice? Right, this is not some like random quantity. This is 1 over 4 pi c squared t squared. What is that? So if someone notices what that quantity is relative to this problem, you can type it in the chat, and I'll get back to it. But this is a very particular choice here of the thing that is being divided by. Not just because, of course, the formula won't work otherwise, although, yeah, that's a big reason. But what I mean is that this expression has a meaning just beyond what is written here, right? Relative to this problem, relative to something else that's showing up here, another quantity that's showing up here. This is a very particular quantity here out front. So what is it that is happening here? Here's Kirchoff's formula. I have fixed x naught, fixed t at some fixed position in time. The displacement is given as some kind of average over a sphere of radius x naught ct. All right, so this is a surface integral over the surface, which is a sphere. And yeah, someone said it in chat. This is the surface area of this sphere, right? So this is a sphere of radius ct centered at x naught. This is the, if you remember correctly, 4 pi r squared is surface area of sphere.